Alright, here we go with the Chapter 5 Homework A review. First of two assignments for this chapter that's all about moles and stoichiometry. So this first assignment did not have any of the stoichiometry topics. It was mostly just relationships involving moles, and there'll be a lot of variations on those as we'll see. The class average this week was pretty good. It was 9.66 out of 12. That's a little bit higher than last time I taught this course, and pretty much in line with what we should see on this assignment. So there were a lot of different types of problems on here, so I probably won't cover everything that you had, but if you have any other questions, please let me know. The other thing to keep in mind on a lot of these questions, not all of them, is that there were many that had sort of variable numerical inputs. So basically Blackboard would randomly assign numbers in the problem that you would use to calculate your answer, and you'd have to type your answer in. So in those cases, you may have had the same problem but with different numbers. So just be aware that it might not look exactly the same, but the series of steps will be the same. If it's the same type of question, you just have to use the appropriate numbers. So let's go into that. I believe this first one was one of those types of problems where you had variable inputs. So there were a few problems on this assignment that actually went back and reviewed stuff that we learned way back in Chapter 1, one of the very first things we learned in the whole course, and it was about mass fraction and mass percents. So what we kind of brought in this chapter was relationships between mass fraction, mass percent, and number of moles, now that we have those definitions in hand. But some of the questions didn't even require that. They were just purely a review of Chapter 1. And I think the reason that they were sometimes difficult is that most likely you tried to make them more complicated than they are. So this is one such problem. This one was requested by a student, but also was one that we didn't do particularly well on as a whole. So here it says a mineral contains only lead and sulfur. A mineral is just a fancy name for compound, a certain type of compound that has it's kind of like an ionic compound. There's nothing to worry about there. But it's just a compound. It contains lead and sulfur. And analysis indicates that a 2.73 gram sample contains 1.47 grams of lead. What is the mass fraction of sulfur in the mineral? Well, here we're giving you masses, and we're asking for the answer as a mass fraction. And so for that, we don't need to even worry about number of moles. We have masses, and we're just going to use them directly. So what we're looking for is the mass fraction of sulfur. Now, we've usually worked more in terms of mass percent, but mass fraction is closely related. So the mass fraction of sulfur, if that's what we're looking for, let's write that out explicitly. It's going to be the mass of sulfur divided by the mass of compound. So the mass fraction is just the ratio of those two. If we were looking for mass percent, which we're not, mass percent is just mass fraction times 100. So that's the relationship between those two. They're very closely related, just one expressed as a decimal, one expressed as a percentage. Okay, but here this is what we're looking for, is this top relationship here. So we need both of these numbers. Now the mass of compound is given, that's 2.73 grams, that's how much of the mineral or the compound we have. But we don't have directly the mass of sulfur. But remember from law of conservation of mass that if your compound contains 2.73 grams, the total mass of the compound is going to equal the mass of the elements that make it up. So if we're looking for the mass of sulfur, which is not directly given, we know that we have 2.73 grams of the compound. We're told that we have 1.47 grams of lead. And the difference then is going to be the mass of the sulfur that's left. So make sure I get that number right. That's going to be 1.26. Alright. Okay, so that's going to be how we get the top part of this calculation. So then finally we're ready to calculate mass fraction, just putting those numbers in. 1.26 grams, which is the mass of sulfur, divided by 2.73 grams, which is the mass of the compound. And since it's a fraction, we don't need to multiply it by anything, we just leave it as that. And that comes out to something 0.4 something, 0.46. I don't remember if Blackboard specified how many decimals should be in your answer, but since our masses were given with 3 significant figures, the mass fraction should be given with 3 also. And it is a unitless quantity because it's grams divided by grams. So this problem, I think, was something we would have learned how to do back in chapter 1. I think we probably most likely just made it more complicated than it is, and we have to remember the definition of mass fraction, which is a little bit different than mass percent, but just related by that factor of 100. Okay, so that was the first one that dealt with that topic, and this one is also very similar, it just takes it one step further. So again, another problem involving a mineral, but this time it contains a metal, M, and fluorine. It doesn't specify what the metal is. Analysis indicates that a sample of the mineral contains 179 grams of metal and 109 grams of fluorine. What mass of fluorine is present in 123 grams of the mineral? Okay, so again, here we're only dealing with masses. We have masses of the two elements in a sample of the compound, and we're looking to find the mass of fluorine in a different amount of the compound. So everything deals with mass ratios, mass fractions. We don't have to worry about moles in this problem. But we have to, again, piece the information together correctly. So we're looking for the mass of fluorine. Now what we should do is we should start with our given information and understand what that means. So in our given information, what we have is 179 grams of the metal combines with 101 grams of fluorine, and those two together, if we add them, would be 280 grams of the compound. So what we can then do is we can establish ratios with any of these amounts. There's 179 grams of metal per 101 grams of fluorine, and there's 179 grams of metal per 280 grams of compound, and so on. So any of these any combination of these two numbers can establish a ratio that defines the composition of this compound. So then we just have to write out what we're looking for. So we're looking for the grams of fluorine that are present in 123 grams of the mineral. So that's going to be our starting point for the calculation we're going to do. We have 123 grams of mineral, and we're trying to figure out how much fluorine is in there. And so what we're going to do is we're going to just multiply this by the appropriate ratio. So we want grams of mineral to cancel, and we're going to find grams of fluorine. And we found from our given information that there's 101 grams of fluorine for every 280 grams of the mineral or the compound. Alright, so we're just going to multiply by that ratio. You could also set this up as a proportionality, as we talked about at the beginning of the course, but I like to do factor label method to make sure that the units work out appropriately. So what we should get, if I did my math right, is 123 grams of the mineral has 44.4 grams of fluorine. Alright, and again, this was a problem where you might have had different inputs in terms of the numbers that you were given for mass of metal, mass of fluorine, and what mass of the mineral you're considering. All those numbers could have been different, but the series of steps would have been the same. So for these two problems, we actually didn't need to worry about moles. These were strictly designed to be a review of chapter 1 and make sure that we're not completely forgetting the concepts that we learned at the beginning. But for the rest of these, we're going to deal with some of the new concepts that were brought in chapter 5. So we had a few questions that dealt with the definition of atomic mass. And so one of the ones that we had here, which I think was requested by a student, is about calculating atomic mass. So we have a certain metal, M, again not specifying what it is, that has 4 stable isotopes. So we give the identities of the isotope, which would be the mass numbers 50, 52, 53, 54, and for each of those isotopes we define the percent composition and the precise atomic mass of that isotope. So the question is asking, what is the average atomic mass of the metal as it would be seen in the periodic table? So it's possible we got tripped up by the wording on this problem. The average atomic mass as it would have seen in the periodic table. What does that mean? Well, that's just the atomic mass. Remember that those atomic masses that we see on the periodic table, those are going to be weighted averages of all of the isotope mass. So all we're looking for here is atomic mass of this metal. And remember what that is going to be the fraction composition of one isotope times its mass, plus the fractional composition of the second isotope times its mass, and so on, however many isotopes we have. So when we're calculating the average atomic mass, it's just a weighted average. You're taking the fraction of each isotope, multiplying by the mass, adding those all together to get the weighted average atomic mass, and that's what we're doing here. Alright, so we have, in this case, 4 isotopes to consider, so we have to make sure we put all of them in with the correct numbers, and again, the percentages have to be written in this case as a fraction to use it. So we're going to take all the percentages and divide them by 100 to get the fractional composition of each isotope. So what we're going to do for this one is, if we're calculating the atomic mass, we're going to take the fraction of the first isotope, which is 4.31%, which comes out to 0.0431 as a decimal, and multiply it by the mass of the first isotope, which is 49.95 AMU. Then we're going to take the second isotope, 52M, that has a fraction of 83.76%, which has a fraction of 0.8376, and then its mass is 51.94 AMU. And then we're going to do the third isotope, 9.55%, so the fraction is 0.0955, and a mass of 52.94. And then the last isotope is a fraction of 2.38%, which comes out to 0.0238, and a mass of 53.94. So remember, all the fractional abundances would add up to 1, all the percent abundances add up to 100, and then when we multiply them by their respective masses and add them, that will give us the atomic mass. So I need to work out the math here for a second, but those are the numbers we're going to put in. So I did not calculate this out ahead of time, so I'm just going to have to calculate this out in real time. I hope I don't mess up. And then, alright, and with the usual caveat that as long as I didn't mess up my math, what I get for this, you would probably want to do this in 3 or 4 significant figures, is 51.997 AMU. So I don't know if the problem specified how many decimal places, but you probably want to add, either use 2 or 3 decimal places here, so you have 51.997 or 52.00. Blackboard for numerical questions is not typically picky about how many decimal places you have, as long as you don't round it too much. And so that's going to be the answer we would enter in. And the number makes sense because you'll notice that our most abundant isotope, the one that's 83.76%, so that's over 4/5 of the composition, has isotope number 52 and a mass of 51.94. So if that's by far our most abundant isotope, then the atomic mass that we calculate should be kind of close to that number, which it is. So it's good to make sure that your answer makes sense. The other thing to do in problems like this where you're calculating atomic mass is you need to make sure that the number that you get is in between the masses of all the isotopes. So it can't be smaller than the smallest isotope as an average, and it can't be bigger than the biggest isotope, and that is certainly true here. So if we had gotten a number that was smaller than 49.95 or bigger than 53.94, the two extremes of the isotope masses, then we would know we messed something up. So again, when you're doing numerical questions, sometimes it takes a lot of time to completely check your work and do all the calculations again. You may not have time to do that on an exam, do the whole problem twice. But it's good to look at your answer and make sure it's at least reasonable, and those are some things you can check on problems like this. All right, and then we get into another question that deals with now formula or molar mass, or molecular mass, all these different terms that mean the same thing for a compound. So that's kind of the previous problem dealt with the definition of atomic mass for an element, and now we're going to deal with some formula masses for compounds. So we have a compound with the formula M3XO44. So again, M is some generic metal, X is some generic nonmetal, not specified. And we want to know if these are the atomic masses of M and X, what is the molecular mass of the compound? So whenever we're calculating molecular mass or molar mass of a compound, it's going to be just the sum of the atomic masses in the formula. Again, sigma means sum. We take all the atomic masses in the chemical formula and we add them up. So in this problem, it's going to be, we have three metals. It's M3. So we have 3 times the atomic mass of the metal. We have, now for X, we have XO4 4 times. So again, what that means when we have a polyatomic ion in parentheses is we have M3, and then that's going to be paired with 4 XO4s. XO4, 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 XO4. So writing it out in more detail, that's the formula of the compound. 3 metals and 4 XO4s. So that means a total of 4 X's. So we need 4 times the atomic mass of X. And then the other one we have is oxygen. So each XO4 has 4 oxygens. There's 4 of them in total. So a total of 16 times the mass of oxygen. So those are going to be the numbers we add up. 3 times the atomic mass of metal, 4 times the atomic mass of X, which is given, and 16 times oxygen, which we have to look up. Alright, so then when we write those out, for the metal it's going to be 105 AMU, that's given in the problem. It's not a real element, so it's given to us. For X, there's 4 of them, and the mass is given as 36 AMU. Again, that's not a real element, so it's given to us. And then for the last one, we have oxygen O, which we have to look up. So 16 oxygen atoms, and the atomic mass of oxygen we can get from the periodic table. Oops, wrong file. So oxygen is here, and the number below, 15.999 or 16.0, which is certainly close enough for this problem. That's going to be the atomic mass of oxygen, the number below it on the periodic table. So 16 times 16 AMU. And so when we add those all together, 3 times 105, 4 times 36, and 16 times 16, we get a big number, 715 AMU. But that would be the molar mass of this fictitious compound. Alright, and again, I think this one may have had variable inputs with the masses of N and X that were given to you, so your number could have come out differently, but you would follow the same series of steps. Alright, so it's not obvious why that problem threw us off a little bit, but I think it's probably just, again, dealing with fictitious elements, which we just have to use the atomic masses that are given to us, not look them up in the periodic table. And also remember that if we have XO4 4, that means we have 4 total XO4 polyatomics, whatever the charge would be for those. And we have to make sure we count for how many total elements are in those, 4 X's and 16 O's being the total. Alright, so that's calculating molar mass for a compound. And then the last several problems I'm going to do all deal with relationships involving moles. And so just different ones here. So this first one here is a pretty straightforward one-step problem. We want to know how many molecules are contained in 9.83 moles of H2O. So if we're looking for the number of atoms or number of molecules in a sample, we should automatically think of Avogadro's number. So we're looking for the number of molecules of water, and we're given that we have 9.83 moles. Remember, Avogadro's number tells us that there are 6.02 times 10 to the 23rd entities, things, whatever you want to call it, in 1 mole. And those, so in water, water is made up of molecules. The formula is H2O. So the sort of simplest unit of water would be 1 molecule of water. And so Avogadro's number will tell us that there's that many molecules in 1 mole. So for this problem here, all we have to do is just multiply by Avogadro's number, because we want moles of water to cancel. We want to find out how many molecules of water are in that many moles. And so we're just going to use Avogadro's number directly. 6.02 times 10 to the 23rd molecules in 1 mole. Alright, and again, since water is a covalent compound, using Avogadro's number tells us how many molecules that compound is made up of. And so when we multiply those out, 83 times 6.02 to 23rd, what we get is 5.92 times 10 to the 24th molecules of water. Okay, so that's how many molecules are in 9.83 moles. Just a one-step calculation this time. But the answer looks for the log in this case again, because especially in olden days, Blackboard wasn't very good at dealing with big exponential numbers like this. So if we take the log of that number, we should get 24 point something, and what we end up with is, hang on, 24.77, and once 3 decimal places, we'd write it as 24.772. Is what I got. I got it to 3 decimals. Okay, so that's the number you would enter into Blackboard. The real answer is this number here. That's how many molecules are in 9.83 moles of water. Then we take the log to enter it in correctly to Blackboard. Okay, so that was a one-step conversion involving moles. But then we also had other problems that involved multiple step conversions. And there's a couple of problems on this assignment that, we didn't really, think exactly about in class. I didn't give examples exactly like this, and it required us to really consider the definition of Avogadro's number and how it relates to the number of, sub-fundamental particles that are making up a specific type of compound. So here what we want to find is how many hydrogen atoms, how many moles of hydrogen atoms are present in 1.72 times 10 to the 24th molecules of CH4. So what we do for this problem is we're looking for moles of hydrogen in this case. So again, in problems like this, it is exceptionally helpful to write out precisely what unit you're looking for. If you just go through and write out a bunch of numbers, punch them into your calculator, you might not know what every number represents, and it's easy to miss a step when you're solving a problem that way. So we're going to write out exactly what we're looking for, which is moles of hydrogen. And we have 1.72 times 10 to the 24th molecules of CH4. So if we have total number of molecules and we want to get into moles, then we just have to use Avogadro's number again, but this time divide by it. Alright, but what we have to again recognize is what does Avogadro's number represent. So if we have molecules of CH4, we want that to cancel out. So we're going to put Avogadro's number in the denominator, and then when we convert that to moles, that's going to be the relationship between the moles of CH4 and the number of molecules of CH4. So we're going to divide by Avogadro's number, which is 6.022 times 10 to the 23rd molecules of CH4 and 1 mole of CH4. Now I suspect that most of you stopped here in this problem. So you did this first step and you go, oh, okay, divide by Avogadro's number, molecules, moles, done. But we have to look closely at what this represents. This is moles of CH4, total moles of methane, CH4 as it's called. We're looking for moles of hydrogen, so we're not done yet. So then what we have to do is do one more relationship, which is if we have a relationship between moles of CH4 and moles of hydrogen. So if we're looking for the moles of one of the elements in the compound, that relationship comes from the chemical formula. So in CH4, the H4 tells us that for every 1 mole of CH4, we have 4 moles of hydrogen. So the last step, which is likely the one that the majority of you forgot if you got this problem wrong, was to multiply by 4, because for every mole of CH4, there's 4 moles of hydrogen. That's what we're looking for here, is moles of hydrogen, not moles of CH4. So we have to make sure we do that last step whenever we're looking for the moles or the number of atoms in a compound, not the number of molecules. We have to account for how many atoms of that type are in the chemical formula. So let's divide those out. So you would have gotten 2.86 moles of CH4, which is probably the number that a lot of you put in, but let's multiply that by 4, and we should get 11.42 moles of H. Alright? So we get 4 times the number of moles of CH4 for the number of moles of hydrogen that we have. Alright, so that was a problem. We didn't do exactly one like that in class, but it requires us to think closely about what exactly Avogadro's number tells us. And Avogadro's number tells us the number of molecules in a mole if we're dealing with a compound that's made up of molecules like CH4. Okay? And then finally, this problem here is going to use the same concept, but also add an additional one in. So here we're looking for the number of chlorine atoms present in 27.5 grams of CCl4, and again we have to enter the log of the answers. This is going to involve a few steps for us because we're trying to find number of atoms, we're given a mass, we don't have a simple relationship between those. But again, start with what we're looking for. We're looking for number of chlorine atoms, and start with what you're given, which is 27.5 grams of CCl4. Alright, So if we're doing a problem that deals with moles or number of molecules, number of atoms, of course the first thing we need to do is get into moles. And so for mass, we're going to use the molar mass to get that. So we need to find the mass of 1 mole of CCl4, which is just going to be its molar mass. So the molar mass of CCl4, or molecular weight as it's often called, is going to be the atomic mass of carbon. So carbon on the periodic table is 12.01 grams per mole, and then 4 times the atomic mass of chlorine, which is 35.45. So here we didn't give you the molar mass of the compound, so you do have to calculate it again. So we're going to use, again, the atomic masses of the 2 elements that make it up. So for carbon, it's 12.01. And then we have 4 chlorines in the formula, CCl4, so we're going to use 4 times the atomic mass of chlorine, which is 35.45 grams per mole. And so when we add those together, we get 153.81. So that's going to be the first step of our calculation, is using the molar mass of CCl4 to convert grams into moles. But we're not done here because we're looking for the number of chlorine atoms, and this is just moles of CCl4. Now from here, there's a couple different order of operations you can do. We can either convert moles of CCl4 into moles of chlorine, or we can convert moles of CCl4 into molecules of CCl4 first. So there's the final 2 steps I'm going to do in this calculation could be done in either order. In reality, you'll get the same number either way because it's the same numbers you're multiplying. But the way I'll do it is, let's now use Avogadro's number. And so for Avogadro's number, we know that there's going to be 6.022 times 10 to the 23rd things per mole. Now again, CCl4 is a molecular compound, so this number is going to tell us how many molecules of CCl4 we have. I ran out of room here, but that's the number of molecules of CCl4 per mole. And again, I think a lot of you probably stopped here. We would have gotten the number this way, but this is the number of molecules of CCl4. We're looking for the number of chlorine atoms. And from the formula of the compound, which can be interpreted in terms of molecules or moles, we have 4 chlorine atoms for every molecule of CCl4. And again, how did I get that number? Well, that's because the formula is CCl4. The little subscript of 4 tells us that 1 molecule of CCl4 has 4 chlorine atoms, or alternatively, 1 mole of CCl4 has 4 moles of chlorine. So however you interpret that number, you'll use it in the same way, but you have to make sure we multiply that factor of 4. So when we do this one, remember that last time multiplied by 4, what we get is 4.31 times 10 to the 23rd chlorine atoms. Now, just to more clearly spell it out, the other way we could have done this problem, which is equally valid, is we start with the same set of steps, convert grams into moles. That's in problems like this that are dealing with moles, that's going to usually be our first step. So we use the same first step. But then the other way we could have set this up is just an alternative way of interpreting and using the numbers would be, if we have 1 mole of CCl4, let's figure out how many moles of chlorine we have first. So that's going to be our 4 to 1 factor, because again, we can interpret the formula in terms of atoms or moles. So 1 mole of CCl4 has 4 moles of chlorine, and then from there we have moles of chlorine. We're looking for number of chlorine atoms, so that we then multiply by Avogadro's number. 6.022 times 10 to the 23rd chlorine atoms in 1 mole of Cl. So all the units cancel out either way, and we get the same number, so I'm not going to write it out again. Now this did ask for the log, so however you chose to calculate the number, that's what you get, and the log of that number let me see. And then the log of that should be 23 And they want 3 decimal places, which it should be, so 634 is what I got. Alright, so that's going to be the way we handle that problem. So it's more steps, but we still have to remember this step here of using the chemical formula to convert between number of molecules and number of atoms in this compound. Alright, so here is a classic problem type on this assignment that many of you had questions about, and I don't blame you. It's the concepts are all things we've dealt with before. It's just how do we use the limited given information we have and get to the answer we want. And so this was one that I, again, didn't cover in class, in part because I don't have infinite time in class, but also because I do think it's beneficial for you guys to see some problems on the homework assignment that you haven't seen in class before and see if you can piece together the concepts we learned and use that to solve an unknown problem type, because this would be one of those. Now there's a missing word here, I'm not sure why I left it out, but a metal oxide with formula M2O contains 11.18% oxygen by mass. I don't know why that number was left out, but that's the mass percent of oxygen in the compound. And we want to type the symbol for the element represented by N. So this seems like not a lot of information. We're trying to find an unknown element, and all we have is a mass percent in a formula. How do we do that? Well, in problems like this, so there's this type of problem that we'll see in this chapter, and then in chapter 6 there'll probably be some other problems that deal with unknown elements as well, or unknown compounds and things like that. Typically the way we're going to do it is, if we want to identify the element, the most definitive way to identify an element is to find its atomic number. But we don't have a good relationship between atomic number and mass and moles and all those things. So we can't really find the atomic number of M, but the next best thing we can do is we can find the atomic mass of the metal M. If we find its atomic mass, then we can go to the periodic table and figure out which element has that specific atomic mass. Alright, so we want to find the atomic mass of the metal, and remember that atomic mass is the ratio of grams to moles. It's how many grams of the metal or any element are in 1 mole of that element. So if we want to find the atomic mass of the metal, the two things we need are the mass of the metal in grams and the moles of the metal. So if we find grams and we find moles, then we can go ahead and divide the two to get the atomic mass. Alright, because again, atomic mass is a relationship between grams and moles. Okay, so then what we're going to do in this problem is we got to find both of those. So because we're given a mass percent, we're going to assume 100 grams of the compound, because then we can interpret the mass percents as gram amounts. So if we have 100 grams of M2O, we have 11.18 grams of oxygen, and then we also have 100 minus that is going to be the mass of the metal. So the mass of the metal in 100 grams, so this is the mass percent of oxygen, the rest has to be the metal M, so we just subtract that from 100. 88.82 is the mass percent of the metal, and that means in 100 grams you have 88.82 grams of the metal. Alright, so again, that's sort of a concept we talked about at the very beginning today. If you have one mass percent or one mass fraction, you can find the other by difference. So in 100 grams of compound, that's how much metal we have. So that's the mass of our metal in 100 grams of compound. And now all we have to do is figure out how many moles are in that same amount of compound. Now we cannot use this number directly to find moles because we don't know the identity of the metal. That's what we're trying to find. But what we do know is the mass of oxygen. That we know the atomic mass of, so we can find out how many moles of oxygen that is, and we can then relate that to the moles of the metal. So here's how we're going to do that. To find the moles of metal, we have 11.18 grams of oxygen in the sample. And then what we can do is we can convert grams of oxygen into moles. As I said in this chapter, when in doubt, convert to moles when you can. So we're going to do that. So 1 mole of oxygen has a mass of 16.00 grams. That's the atomic mass from the periodic table. So now we know how many moles of oxygen there are, and to get the moles of metal, we're going to use the chemical formula M2O. So what the chemical formula tells us, if we want to find a relationship between the moles of metal and moles of oxygen, the formula is M2O. 2 moles of metal for every 1 mole of oxygen. Alright, and so we use that to figure out how many moles of the metal there are. There's twice as many moles of metal as there are oxygen, because the formula is M2O. And so that comes out to 1.398 moles of metal. So then we're going to put that number in here to calculate the atomic mass. 88.82 grams, that corresponds to 1.398 moles that we just did the other calculation, and then dividing those two is 63.53. So that's the atomic mass of M, but this is looking for the identity, the symbol of M. So what you do is go to the periodic table and figure out which metal has the atomic mass that's closest to 63.53. Okay? So if we go to the periodic table, we find atomic masses in the bottom. They get bigger, 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 bigger. And then here, copper is 63.55. So that's pretty darn close to the number I got, 63.53. So that's going to be the correct identity for the metal. So you might not get exact, correlation, but for copper, we find that on the periodic table, it's 63.55 grams per mole. That's pretty darn close to that number there. So copper would be the identity of the metal that is represented by this information here. Okay, so it was, a little bit hard to get the problem started. We have to know what to do with that information, but now that you've seen it, hopefully it becomes very clear that it's just, using relationships we've already learned. Mass percentages to find out the mass of one of the elements in the compound, and then in relationships involving mass and moles and chemical formulas to find the number of moles of that element in the compound. Alright, so that was that question there. I had a lot of people had questions on that one, so make sure you know how to do it and ask me anything if there's something that's unclear. Alright, the last question here, and I forgot to write out the answer choices, so give me a second to pull it back up, is which of the following has the greatest number of atoms? So what we have is 1.0 moles of helium, B is 0.60 moles of H2, so this is a multiple choice question, C is 20 grams of potassium, D is, let me write this on the next line. D is 8.5 milliliters of water, and we're given the hint that the density of water is 1, which you should know, but we're giving it to you here as a hint. So 1 gram per milliliter is the density of water, and then the last answer choice is 22.6 grams of KMnO4. Okay, so there's a lot of calculation you have to do in this problem, unfortunately. There's no real shortcut around it. You have 5 answer choices, and you have to figure out which one has the greatest number of atoms. So technically speaking, we need to calculate the number of atoms in each of these answer choices. Now the reality, though, is we could just do it as, we could just calculate the moles of atoms. That'll be a smaller number to deal with and one fewer step in most cases, because if we calculate moles of atoms, to get number of atoms, we would just multiply that by Avogadro's number. So whichever of these has the largest number of moles of atoms is also going to have the largest number total of atoms. So you could go through the full series of steps and calculate the number of atoms in each of these, but then you'd be comparing large numbers with exponents, and it's easier to make a mistake on those. So I think it's a little bit simpler to just calculate the one that has the most number of moles of atoms, and that one would also be the one that has the largest number of atoms. So for each of these, we're going to do that. So if we have 1 mole of helium, we're going to calculate the number of total atoms in each of these. We have 1.0 moles of helium, rather for moles of atoms, sorry. The moles of atoms and 1.0 moles of helium, it's just going to be 1.0 moles of atoms. Because helium is made up of atoms, so if you have 1 mole of helium, you have 1 mole of atoms. It's an atomic element just made up of helium. For choice B, for 0.06 moles of H2, we look for the moles of atoms in that. We have 0.60 moles of H2, but the formula is H2. There are 2 moles of atoms for every 1 mole of H2. Right? Because again, each hydrogen is made up of 2 atoms. I need to pause this for a second, something just came up. Alright, back from my unplanned break to finish off this last beast of a problem. So we found out that in hydrogen there are 2 moles of atoms per every mole because it's H2. So that means we have 1.20 moles of atoms. Or if you want to find the number of atoms, it would just be that times Avogadro's number. For choice C, we have 20 grams of potassium. So, potassium is an element with formula K, so any element that's not specified as being diatomic like H2 or polyatomic like P4S8, it's just going to be made up of atoms. So if we have 20 grams of potassium, looking for moles of atoms in that, so we go to the periodic table to find the atomic mass of potassium, which is 39. I mean, pretty close to 40 if we want to round it. We'll be more exact than that. So we have 39. 1 mole of potassium is 39 grams. That's the atomic mass. And then we have, again, potassium is made up of atoms, so we don't have to do this last step, but 1 mole of atoms for every mole of potassium, because potassium is just K, the formula. So that's going to be about 0.5, and it's going to be smaller anyway. So it's like 0.51 moles of atoms in 20 grams of potassium. Alright, and then choice D, this is one we haven't done a lot with, density, but we should know how to use it as a ratio of mass to volume. So if we want to find the moles of atoms in H2O, we have 8.5 milliliters. We can get into mass by using the density, 1 gram per milliliter. So we're just using density as a conversion factor. So that number is the same, it's just a density of 1 for water. So if you have 8.5 milliliters, you also have 8.5 grams. Once we have grams, we can find moles of water by using its molecular mass, which is 18. So H2O, 2 hydrogens, 1 oxygen, is a total of 18 grams per mole. But that's moles of water molecules, but we want to find moles of atoms. You have to recognize that the formula of water is H2O. So the total of 3 moles of atoms for every 1 mole of water. So water is made up of H2O molecules, so we have 3 moles of atoms total, 2 hydrogens, 1 oxygen for every mole of water. So when we multiply that out, 8.5 divided by 18 times 3, we get 1.4 moles of atoms. So that's our biggest number so far. And then the last one is KMnO4. So this is going to be a similar calculation, but we're starting with mass this time instead of density, so that instead of volume, so that makes it a little bit simpler. So we have 22.6 grams of KMnO4. Now we do have to use the molar mass of KMnO4 to get into moles. So I didn't give you that number here, so we're going to have to go through and quickly calculate it. So KMnO4, K is 39. We don't need real precise numbers here. Manganese, Mn is 55. And then we have 4 oxygens, which is 4 times 16. So the molar mass of KMnO4 is about 158. So I did that quickly, but you can check yourself and make sure you get that. So 158 grams per mole for KMnO4. But again, that's moles of KMnO4 formula units. It's not really a molecular compound in this case because it's ionic, but nonetheless, it's this many moles of the formula KMnO4. But if we're looking for moles of atoms, the formula has 1, 2, 3, 4, 5, 6. KMn, 4 oxygen, total of 6 moles of atoms for every mole of KMnO4. So we have to multiply that by 6. We've seen that step now a few times in this assignment. And so what we get for that is still a smaller number, 0.86. if we're using sig figs correctly, 858 moles of atoms. Alright, so the number that ends up being biggest is this one here. So choice D, which is 8.5 milliliters of water, is going to be the one that has the most atoms. So here I calculated moles of atoms. Again, to get the number of atoms, you just multiply each of these by 6.02 times 10 to the 23rd, Avogadro's number. So you don't need to necessarily do that last step. So it has the most number of moles, it's going to have the most number of atoms, because that's just a counting number. That would be the same for all of them. But we have to, again, remember to use chemical formulas in the cases of compounds like water and KMnO4 to figure out how many moles of atoms are in there, because the initial calculation will just give us the number of molecules or number of formula units. Alright, so that question was kind of complicated, but I wanted to go through it because it sort of reviewed a lot of the relationships that we covered in this assignment. Again, go through these. These are a lot of important relationships that we'll keep using over and over again, so make sure you're very comfortable with them. And if there's anything else that you want me to go over that I didn't cover, or if there's any of these topics that you're still unclear on, please come find me and get some help, and we'll try to get that squared away as soon as possible. Alright, I'll see you guys in class tomorrow, and have a good rest of your week.